Hello everyone, I'm Norman Wildberger. In today's famous math problem, we're going to go back to Leonhard Euler and a very important and famous and beautiful formula or relation that he found between the vertices, the edges, and the faces of the Platonic solids. Alright, so the 5 Platonic solids have been studied and admired since antiquity. And there are 5 of them. They're sometimes also called the regular solids. And the regularity has to do with the fact that, first of all, their faces are each regular polygons. So in the case of the tetrahedron, we have equilateral triangles. We also have equilateral triangles for the octahedron and for the icosahedron. The cube is made up of square faces, and the dodecahedron is made up of pentagonal faces, regular polygons in each case. Alright, so the tetrahedron has these 4 faces that fit together in a nice way. The cube, familiar to pretty well everyone. The octahedron, there it is there. It has 1, 2, 3, 4, 5, 6, 7, 8 triangular faces. The icosahedron and the dodecahedron are a little bit more complicated and fancy. This one here, the icosahedron, is made up of triangular faces, and it has 20 triangular faces and 12 vertices. And the dodecahedron is made up of these pentagonal faces, and there are 12 of them and 20 vertices. Okay, so they've been studied since antiquity. We're going to talk a little bit about their story. But the interesting thing for us today is a question that Leonhard Euler posed to himself. He said, all right, people have been studying these things for thousands of years. I want to understand the relationship between the numbers of vertices, edges, and faces for any one of these solids. In other words, he tabulated something like this, a table that shows us for each one of the 5 regular solids how many vertices it has, how many edges it has, and how many faces it has. So for example, the octahedron has 1, 2, 3, 4, 5, 6 vertices. So here on this row, the octahedron row, 6 vertices. And it has 12 edges. The edges are the sides where the 2 faces that are adjacent meet, connecting adjacent vertices. So here's an edge. There's another one, there's another one, there's another one. There's 4 emanating from this vertex down here. There's also 4 emanating from the vertex on top. And then there are 4 edges in this middle layer for a total of 12. And we've already remarked that there are 8 faces. So similarly, it's not too hard to make a model of any one of these and then to actually count. So the tetrahedron has 4 vertices, 6 edges, and 4 faces. The cube has 8 vertices, 12 edges, and 6 faces. The octahedron, we've just said, has 6 vertices, 12 edges, and 8 faces. The icosahedron has 12 vertices, 30 edges, and 20 faces, while the dodecahedron has 20 vertices, 30 edges, and 12 faces. And Euler was the first one to ask himself the simple but really quite natural question, what is the relation between these 3 numbers for any one of these solids? Or to put it another way, suppose that one of these numbers got removed, accidentally got rubbed off. Could we determine any one of these numbers from knowing the other 2? It's another way of saying it. If you knew the number of vertices and the number of faces for one of these, what would the number of edges be? So here then is our famous math problem number 15, which was posed in 1750 by Euler. It is, what is the relation between the number of vertices, called V, the number of edges, denoted E, and the number of faces, denoted F, of a Platonic solid? And I give this problem a difficulty of between 1 and 5, a rather variable difficulty. And the reason for that is because for the case of the Platonic solids, it's not too hard to determine what the relationship is. But it turns out that the relation holds, as Euler realized, more generally. So an extension of this problem is to show that the same formula, whatever it is, holds also for a general convex polyhedron. So not just for the 5 Platonic solids, but in fact any polyhedron that is essentially convex, or that roughly has the shape of a sphere. Okay, so Euler mentioned this problem in a letter to his friend Christian Goldbach in 1750, and he struggled for a few years to give a complete proof of it. After Euler, Legendre gave a better proof, and that really sort of propelled it into the mainstream of mathematics. Later, Poincaré realized the essential topological aspect of the statement. I should also mention that a similar kind of circle of ideas had been worked on by Descartes more than 100 years before Euler. And some people have suggested that perhaps Descartes essentially had this formula. And there's some evidence to suggest that, but probably overall we have to say that Descartes didn't quite understand the formula in the right way. Okay, so at this point, I'm going to leave it to you as an exercise. So most of you who are watching this, of course, will have seen this formula before. But for those of you who have not, okay, this is a great place to actually do a little bit of investigation on your own. So I strongly suggest that if you have not seen this formula before, please halt the video, go back to that table that I showed you in the first slide, and stare at it for an hour or two, or maybe just 10 minutes, and see if you can find the relation that holds between V, E, and F for each one of the Platonic solids. So the same relation holds for all 5 Platonic solids. And see if you can discover that on your own, just as Euler would have done more than 250 years ago. All right, so without more ado, here is Euler's polyhedral formula, one of the most important and beautiful formulas in all of mathematics. It's that the relationship between the number of vertices, edges, and faces of one of the Platonic solids is that V minus E plus F always equals 2. And this particular combination of vertices minus edges plus faces is often given the Greek letter chi, sometimes called Euler's number, or sometimes the Euler characteristic when we talk about topological things. All right, so let's verify that it's actually true. So for the tetrahedron, the numbers V, E, and F are 4, 6, and 4. And yes, we can check that 4 minus 6 plus 4 does indeed equal 2. For the cube, 8 vertices minus 12 edges plus 6 faces equals 2. For the octahedron, 6 vertices, 12 edges, 8 faces. That combination equals 2. For the icosahedron, we get 12 minus 30 plus 20 equals 2. And the dodecahedron, 20 minus 30 plus 12 equals 2. It might be, at this point, a good place to mention that there's some kind of symmetry between these 5 objects. You can see that the cube and the octahedron's formulas are pretty close to being the same. They have the same number of edges, and the number of vertices of one is equal to the number of faces of the other. A similar kind of symmetry holds between the icosahedron and the dodecahedron. They both have 30 edges, and the number of vertices of one equals the number of faces of the other. The tetrahedron is somehow self-dual in that sense, in that its number of vertices equals its number of faces. And if you think about it a little bit geometrically, you see that this is not a big surprise because these two are naturally in kind of duality with respect to each other, as are the icosahedron and the dodecahedron. And the simplest way of seeing that is to take one of these four, say the cube, and imagine creating a new polyhedron by taking the center of each of the faces as a new vertex. So you imagine having a cube, and then you take the centers of each face and making those the vertices of a new object, you're going to get an octahedron. And the same thing is true, you can check, for the icosahedron and the dodecahedron. The way that explains this pairing that occurs with these numbers. But Euler realized remarkably that his formula did not just hold for the 5 Platonic solids. It's very nice for the 5 Platonic solids, but it holds more generally. In fact, its generalizations go far, far beyond the Platonic solids, go up eventually to higher dimensions and to very modern theories, even of differential geometry, algebraic topology, and modern physics. So the ramifications and extensions of this simple-looking formula are very significant indeed. Let's say a few words about the history of the Platonic solids that go back to the very beginnings of mathematical thought. So the ancient Greeks valued the Platonic solids very highly. And in fact, the earliest of the ancient Greek thinkers, which were the Pythagoreans, they were already aware of the tetrahedron, the cube, and the dodecahedron as interesting and important mathematical objects. And that was around 500 BC, so the followers of Pythagoras. A little while later, Theaetetus of Athens, who lived from 417 to 369 BC, and was sort of a student of Plato, he really studied these 5 solids very carefully. He proved that there were 5 regular solids altogether, and extended the list to include the octahedron and the icosahedron. And in fact, book 13 of Euclid's Elements, which is the final, sort of penultimate book of that series, deals expressly with the 5 Platonic solids. And probably most of that material of Euclid was taken from the work of Theaetetus. Okay, so what makes one of these solids a Platonic solids? What makes it regular in the right way? So, well, each one of these solids has a large amount of symmetry that defines it. And it's interesting to lay out what the symmetry is. So, for something like the cube, for example, we see that, first of all, that each face is a regular polygon. Okay, this is a common feature of all the Platonic solids. Each of the faces itself is a single regular polygon, and they're all the same size and shape. And each face plays an identical role. In other words, there's no way you can tell one face from another. For example, if we marked these faces, say this is face number 1 and face number 2, and then someone came along and rubbed off those markings and rotated the thing around, we would not be able to, just looking at the geometry, to tell which one was the face that we labeled 1 and which one was the face that we labeled 2. Without any markings, all of the faces look exactly the same geometrically. There's a symmetry between the faces. And in fact, the same holds for all the edges. Any one edge looks just the same as any other edge. And in fact, the same thing holds true for each of the vertices. Any one of the vertices looks just the same as any of the other vertices. So there's a very strong and almost complete symmetry between the faces, the edges, and the vertices in these regular solids, in the 5 Platonic solids. And there are only 5 of them. That was proved by Theaetetus. But why are they called the Platonic solids then? Well, Plato, who was a famous philosopher, thinker, writer, and also a very strong advocate of mathematics, he published a series of dialogues that became very famous. And one of them was called Timaeus. And in that he has a dialogue between various people, including Socrates and this fellow called Timaeus. And they discuss these Platonic solids, amongst other things. So it's because of Plato's work here that the Platonic solids became sort of widely known in the more general community. And back then, there was a kind of interpretation or theory that these 5 Platonic solids probably had something to do with the very fundamental makeup of the natural world. So the ancient Greeks identified the 4 sort of elements, fire, air, earth, and water, with 4 of the Platonic solids. So fire was considered sort of to be made up of tetrahedrons, air of octahedrons, earth of cubes, it's kind of solid, and water of icosahedrons, which is sort of more like a ball, can flow a little bit more. You might ask, well, what about the dodecahedron? Because there's actually 5 of them, not 4. Well, from their point of view, the dodecahedron was sort of the most magical and biggest and universal of all of them. And it was deemed to be playing the role of the universe itself. The universe itself was some kind of dodecahedron in which these other 4 somehow were superimposed. All right, so this is a very simplistic view of chemistry, which we don't ascribe to today. But nevertheless, the interest of these Platonic solids has maintained itself over millennium. So while the Platonic solids are sort of the jewel in the crown of ancient Greek geometry, there were other symmetrical solids, polyhedron, that they also investigated. So Archimedes in particular investigated some solids that also were quite regular, but not quite as regular as the Platonic solids. So an Archimedean solid has faces which are also regular polygons, but we are allowed to have more than one type and shape of face. We'd still want that each vertex is identical to any other. All right, there's an interesting list of Archimedean solids, and we'll talk about them. It's an interesting problem of classifying them, as well as the interesting problem of classifying Platonic solids. It's also a very famous problem we'll talk about at some point. But to give you a sense of an Archimedean solid, what you can do is you could take one of the Platonic solids, say the cube, and you can truncate or chop off a little area around a corner or a vertex. So if we take one of these vertices here, there are 3 edges coming out. If we snip a triangular piece away, make cuts here, here, and here, and chop that off with a little plane, and we do the same thing symmetrically around each one of the vertices, then we're going to get a new solid which has faces which are, well, these could be these triangular faces which we're cutting out, and then the original squares are replaced with octagons. And if we cut these triangular pieces out of the right size, then we can make this side and this side the same, so that this will be a regular octagon. So this kind of truncated cube has faces which are equilateral triangles and octagons. Okay, so Euler realized that his formula works also for these more general kinds of polyhedron. And let's just check it here. So how many vertices does this truncated cube have? Well, for each one of the original vertices of the cube, we've created this little triangle, making 3 new vertices to replace the original one. So there were 8 original vertices, so there are now 24 new vertices. And how many edges does the new object have? Well, each of the original edges still contributes an edge, but we also have 8 times 3 new edges, because each one of these triangular pieces that we cut off contributes 3 more edges. There's 8 of them, so for a total of 36 edges altogether. And how many faces are there? Well, the original 6 faces are still there, although they're octagons rather than squares. And then we've created 8 new triangular faces around the original corners for a total of 14. And so if we check the Euler number, V minus E plus F, that particular combination, is 24 minus 36 plus 14. And lo and behold, we still get 2. All right, so here's an exercise for you. Make the same computation with the appropriate truncations of the other Platonic solids. So have a think about how you would truncate the other Platonic solids to make an Archimedean solid, one whose faces are still regular polygons. And for each one of them, compute vertices, edges, and faces, and check to make sure that this combination V minus E plus F still gives us 2 in each of the cases. So although Euler realized that his formula worked for more general polyhedra, an exact kind of definition and pinning down of what the word polyhedron actually completely means eluded him. And that was perhaps part of the reason why he had some difficulty in actually proving his theorem completely to his satisfaction. It turns out that there are sort of degenerate or special kinds of configurations that one can cook up that it's debatable whether we should call them polyhedron or not. For example, suppose you take one tetrahedron and another tetrahedron and you bring them together with their 2 vertices touching. Are you going to call such a thing a polyhedron? Well, it's still made up of triangular faces and so on. But okay, whether it is or it isn't, it depends on your setup. But in any case, I guess it was realized eventually that the theory works in a very nice way if we restrict ourselves to convex polyhedron. And those are ones which can be represented on a sphere. Let me explain what that means. So we're going to go from one of these solids with polygonal faces to actually just a sphere. So here's a sphere. And we're thinking about replacing a cube, okay, with its image on the sphere. You can imagine you're inside a cube, maybe right in the middle, and you're projecting that cube onto a surrounding sphere. Then the image of that cube on the sphere would be something like this. So hopefully you can see 8 points. There's 4 on the side of the sphere that's facing us, and then there are 4 on the other side, given by these little empty circles. And the sides of the cube are sort of great circle arcs, maybe something like this. There's one square side, and then another side would be one formed by these vertices, okay, that would wrap around this side. So there's 2 that wrap around on this side, and then there's a top here and a bottom here, and then there's one at the back which is there with those dotted lines connecting those 4 in the back. Okay, this is still a valid representation when it comes to numbers of vertices, edges, and faces, because the numbers of vertices, edges, and faces here are just the same as they were on the original polyhedron. Okay, so this maintains these numbers, so this Euler characteristic is still going to be 2, even if we're counting now this configuration on the sphere. So now that the faces are replaced by regions on the sphere, we might even think of them as something like countries. This is a map. These are the borders between countries. These are countries, and any 2 countries are adjacent along a common edge. Okay, sort of the convention. So it turns out that if we restrict ourselves to this kind of polyhedron that can be represented on the sphere, then our understanding of the formula and why it's true can be significantly simplified. Okay, so here's an idea of a proof, which is a proof that uses some basic notions from graph theory. The first step is to project the sphere onto a plane. And this is sometimes called stereographic projection. It's a kind of a way of representing a spherical map as a planar map. And the way we do that is we take our sphere and we take one of the faces, say this square on this side, and we choose a point inside it. say that green point there. And that's a point that's supposed to be on the surface of the sphere, but in the middle of one of the countries. And then we take a plane, which is perhaps on the other side of the sphere. Doesn't really matter so much where it is. And we're just going to project the graph of the countries, the map, onto the plane by drawing straight lines from our projection point. So this vertex here, well, we'll draw a straight line from the green point to this one here until eventually we reach the plane, and then we draw the corresponding point over here. Well, this point at the back here, for example, another straight line through that one to that point there. So what we get is we get an image of the spherical map as a planar graph now, where the various map regions are now corresponding to regions in the plane, with the important observation that the original face that contained the projection point now corresponds to the outside of this graph. So the points that were in this face here are corresponding to the outside. So if we count vertices, edges, and faces, there are still 2, 4, 6, 8 vertices. There's still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And in terms of faces, there are 1, 2, 3, 4, 5, 6. Still 6 faces if we agree to include the outside of this planar graph. So we're sort of flattening the sphere to give us a planar picture that we can work with a little bit simpler than it's just there in front of us on the plane. All right, so our aim is to prove Euler's formula, and our first step is to project onto the plane. And our second step is to remove edges belonging to cycles. So a cycle is a part of a graph where you have one edge, followed by another edge, followed by another edge, where you eventually come back to the starting point. So for example, in this example here, there's a bunch of cycles. Here's one cycle. This edge, this edge, this edge, this edge. That forms a cycle. Here's another cycle. 1, 2, 3, 4. Another one would be 1, 2, 3, 4, 5, 6, and so on. Okay, what we're going to do now in this second step is to remove edges from cycles. Okay, that's still going to keep the graph connected. Right now we're starting with a connected graph. If we remove an edge from a cycle, because there's a cycle going from one vertex to another, then removing an edge is still going to keep it connected. But more importantly, it's not going to change this quantity that we're interested in. The combination vertices minus edges plus faces is not going to change, because if we remove an edge, okay, then in a cycle, we're also decreasing the number of faces, because the face on this side of that edge and the face on this side of that edge are different faces, because we're assuming that this edge, say, is part of a cycle. So it's part of this cycle here. So that face and that face are different. So when we remove this edge going from here to here, it's gone now. These two faces, which were originally separate, have now been melded into one face. So when we do this operation, the number of edges goes down by 1 at each step, and the number of faces goes down by 1 in each step. So if this number is decreasing by 1 and this number is decreasing by 1, then because there's a minus sign here and a plus sign here, the combination V minus E plus F is unchanged. Right? So this simple operation of dropping an edge from a cycle keeps this Euler number unchanged. Okay, so for example here I've removed one edge, then from here to here I've removed this edge. This edge is still part of a cycle, say it's part of that cycle there, so I can remove it. When I remove it, then it's gone. And also these two faces, which were originally distinct faces, are now melded into one, so the number of faces has decreased also by 1. And here I'm just counting the number of vertices, edges, and faces in each one of the 3 diagrams. And you can see that the number of edges has gone down, the number of faces has gone down by 1 in each case, and the Euler number has not changed. So whatever it is here, it's still going to be the same here after we perform this operation. And we're going to continue to do this. We're going to continue to identify edges that belong to cycles, and whenever we can find a cycle, we're going to remove an edge. We're going to keep doing that until there are no more cycles. Okay? And if there are no more cycles, then we get a graph which is called a tree. We've talked about trees earlier in this series. All right, so that's what we're going to do. We're going to keep performing this step until eventually there are no more cycles, and now we're in the situation where we have a tree. All right, now our third step in the proof is to remove an extremal vertex and its associated edge. Let me illustrate that here. So suppose we're at this stage here where we have a tree. So there are no more cycles. We still have vertices and edges. We're going to identify an extremal vertex. By that I mean a vertex which has only one edge coming into it. So for example, here is an extremal vertex. All right? There's only one edge coming into it, not 2 like here or 3 like here or more. So here's an extremal vertex. Here's another one. Here's another one. We're going to pick one of these and we're going to remove that vertex and also the edge that comes into it. So you go from here to here, we're removing that vertex and removing the edge. Because this is an extremal edge, okay, removing it is still not going to change the connectivity of this tree or this graph. It's connected here, it's still connected here. And more crucially, it doesn't change this combination v minus e plus f, because we're decreasing the vertices by 1 and we're decreasing the edges also by 1. It's the same argument that we had in the previous step where we decreased these two. Now we're decreasing each of these two. This is going down by 1, this is going down by 1. So the combination v minus e plus f does not change. So whatever it was at the beginning, it's going to stay the same whenever we do this. So at this stage here, I'm removing this extremal vertex and this associated edge to get something like this, and we keep on going. At each stage, the Euler number is not changing, and our tree is getting smaller and smaller and smaller, and staying connected. Well, eventually, there's only one final position that we can get. The final position is when there are no more extremal vertices with edges coming into it. In other words, when there's only one single vertex left. In this final situation, there is one vertex, 0 edges, and one face. F equals 1. And now the Euler number v minus e plus f is then 1 minus 0 plus 1, which is 2. So at this final position, we can calculate the Euler number completely. And at every stage, we have not changed the Euler number. So the Euler number that we started with back when we had our map on the sphere must also have been 2. That's the proof why Euler's number works for a convex polyhedron. It really is a lovely argument, and it's a fabulous formula. And we'll see later on in this series that, that the Euler characteristic also extends to other interesting kinds of topological spaces. If you're interested in this sort of circle of ideas, I suggest that you have a look at my algebraic topology series. Okay, so somewhere in the middle there, I talk quite a bit about Euler characteristic and go into more detail and talk about how it's connected with, well, the topology of other more general surfaces. So you might find that interesting if you've enjoyed this talk and want a little bit more. All right, so in our next famous math problem, we're going to go back to Archimedes. And we're going to talk about a very interesting and important problem, which very fundamental really, which is how to find the area of a triangle from its three sides. Very important historical problem. And there's an interesting twist to this problem that's really only been discovered in modern times. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.